The use of radioisotopes. A tracer is a substance that reveals its presence in one way or another and thus can be localized or monitored during the course of an experiment. Be fluorescently labeled, spin labeled, density labeled, or radioactively labeled. In each case, a labeled group enables a molecule to be detected without affecting the specificity of its interactions. Radioactive molecules, for example, participate in the same reactions as non-radioactive species, but their location can be followed and the amount present can be measured. So their peculiarity is that they just undergo the same reactions as non-radioactive species, but still we can trace them, their location, and they can be followed, and the amount present can be measured. So this helps in the tracing of this radioisotopes, which is very beneficial. The identity of an atom, whether it be an iron atom, a chlorine atom, or some other type, and this its chemical properties is determined by a number of positively charged protons in its nucleus. All hydrogen atoms have a single proton, all helium atoms have two protons, all lithium atoms have three protons, and so forth. Not all hydrogen, helium, or lithium atoms, however, have the same number of neutrons. Atoms have the same number of protons and different number of neutrons, as said to be isotopes of one another. Even hydrogen, the simplest element, can exist as three different isotopes depending on whether the atom has 0, 1, or 2 neutrons in its nucleus. Of these three isotopes of hydrogen, only the one containing 2 neutrons is radioactive, that is tritium. Tritium. Isotopes are radioactive when they contain an unstable combination of protons and neutrons. Atoms that are unstable tend to break apart or disintegrate, thus achieving a more stable configuration. When an atom disintegrates, it releases particles or electromagnetic radiation that can be monitored by appropriate instruments. Radioactive isotopes occur throughout the periodic table of elements and they can be produced from non-radioactive elements in the laboratory. Many biological molecules can be purchased in a radioactive state, that is containing one or more radioactive atoms as part of their structure. The half-life of a radioisotope is a measure of its instability. The more unstable a particular isotope, the greater the likelihood that a given atom will disintegrate in a given amount of time. If one starts with 1 curie of tritium, 12 years which is the half-life of this isotope. In the early years of research into photosynthesis and other metabolic pathways, the only available isotope of carbon was 11 carbon, which has a half-life of approximately 20 minutes. Experiments with 11 carbon were literally carried out on the run so that the amount of incorporated isotope could be measured before the substance disappeared. The availability in the 1950 of 14 carbon, a radioisotope having a half-life of many years, about 507 5,700 years, has greeted with great celebration. The radioisotopes of greatest importance in cell biology research were listed, like many of them are listed, along with the information of their half-lives. Three main forms of radiation can be released by atoms during their disintegration. The atom may release an alpha particle, which consists of two protons and two neutrons and equivalent to the nucleus of a helium atom, a beta particle, which is equivalent to an electron, and a gamma radiation, which consists of electromagnetic radiation or photons. The most commonly used isotopes are beta emitters, which are not monitored by either of two different methodologies, liquid scintillation spectrometry or autoradiography. First is the liquid scintillation spectrometry. It is used to measure the amount of radioactivity in a given sample. The technique is based on the property of certain molecules termed phosphorus and scintillance to absorb some of the energy of an emitted particle and release this energy in the form of light. In preparing a sample of liquid scintillation counting, one mixes the sample with a solution of a phosphor in glass or plastic scintillation vial. This brings the phosphor and radioactive isotope into very close contact so that radiation from even the weakest beta emitters can be effectively measured. Once mixed, the vial is placed into the counting instrument where it is lowered into a well whose walls contain an extremely sensitive photodetector. An radioactive atom within a vial disintegrate and emits particles activating the singulators which emit flashes of light. The light is detected by a photocell and the signal is amplified by a photomultiplier tube within the counter. After correcting for background noise, the amount of radioactivity present in each vial is displayed in a printout. Autoradiography is a broad-based technique based used to determine where a particular isotope is located, whether in a cell or a polyacrylamide gel or on a nitrocellulose fiber. The importance of autoradiography in early discoveries on the synthetic activities of cells were described in the pulse chase experiments, and autoradiography takes advantage of the ability of particle emitted from radioactive atom to activate a photographic emulsion, much like light or X-rays activate the emission that coats a piece of film. If the photographic emulsion is brought into close contact with the radioactive source, the particles emitted by the source layer leave tiny black silver grains in the emulsion after photographic development. Autoradiography is used to localize radioisotopes within the tissue sections that have been immobilized on the slides or TEM grid. The steps involved in the preparation of light microscopic autoradiograph is shown. The emulsion is applied to the sections on the side or grid as a very thin overlying layer. The specimen is put into this light-proof container to allow the emulsion to be exposed by the emissions. The longer the specimen is left before development, the greater the number of silver grains that are formed. When the development of slide or grid is examined in the microscope, the location of the silver grains in the layer of emulsion just above the tissue indicates the location of the radioactivity in the underlying cells. So when we just try to learn the process, that is steps taken during the preparation of light microscopic photoradiography, we can see incubate cells in radioactive compound, wash and fix cells in fixative, and after that dehydrate and embed cells in wax or plastic section wax or plastic block, and later that plastic section cells will be there, and then just dip the slide into the liquid emulsion. After that section is there, dipping vessel is there, and dip slide into the radiation sensitive emulsion in the dark room and store slides in dark box until ready to process. And then develop the top view can be seen the like silver grains over cell, black background, silver grain, slide after processing. Like when we just view the side view, layer of emulsion will be there, slide will be there, section is there, cell is there, and silver grain is associated with that. So as a process, we will be first starting with incubating the cells in radioactive compound, later washing and fixing cells, then cells in a fixative and dehydrate and embed cells in wax or plastic, then section wax or plastic box. Along with that, plastic section cells are there, and just dip that into radiation sensitive emulsion in the dark room and keep there for many days. And after that, store slides in the dark box until ready to process, and then process that and just view the slide. There are silver grains over cell, black background, silver grain will be also there. So this is a process of autoradiography which measures the helps us to visualize the radioactivity of underlying cells.